Hello everyone, today we will present our mini project on forecasting engineering. So here are our teammates. Our project consists of 4 main tasks. I will start with task 1. First, let's look at our data source. We collect the data on retail sales of beer, wine, and liquor stores from Freight database. The timeline is from 1992 to 2025. Before analyzing, we had to clean the data. The most important step was to make sure all data sets align with the same timestamp so we could run the regression model correctly. Next, let's look at the histogram. The statistics suggest that the data are right skews. The skewness value is positive, so the distribution has a long tail on the right, especially the point estimate to mean is larger than the medians. This means that some relative high observations pull the mean upward. This is typically of right skew distributions. The box log also gives us more details. First, the data is non-stationary. It doesn't stay around a stable average, but fluctuates a lot. Second, the data are quite spread out. You can see the outliers marked with X symbols on the right. This represents unusual high sales value that contribute to the right skewness we mentioned earlier. For the next questions, does the data follow a normal distribution? We use Anderson's-Darling anomaly test. The p-value is less than 0.0005 because this is smaller than the alpha. We conclude that the data does not follow a normal distribution. Also, the CV is about 43%, which is high. This confirms that the sales data varies significantly. Since this is not normal, we try to find the best distributions that fit our data. We test many types. Unfortunately, according to the goodness of fit tests, none of them were perfect, so we compare to the AD score. The two best candidates were the 3-parameter Weibo and the 3-parameter gammas. So to confirm the decisions, we look at the probability plots. So please look at the graph. We can see that the blue data points for the 3-parameter Weibo cluster are closer to the straight red line compared to the gamma distributions. Therefore, we choose the 3-parameter Weibo distributions is the best fit our data. That's the end for the task 1. Okay, bye-bye.
So I'm gonna talk about task 2. In order to analyze the time series patterns, we draw a time series plot in an ACF graph. So from the plot, you can see that the data exhibit a clear upward trend over the years. In about seasonal variation, there are peaks and troughs at 12 months interval, indicating a seasonal period of 12. And in the ACF graph, there are peaks after every 12 legs, confirming the seasonal cycle. Also, first several legs have very high values and slowly decayed, proving there's a trend in the data. In order to determine whether the data is multiplicative or additive, make a differencing of order 1 to the data, y of t minus 1 to detrend the data. And from the time series plot after differencing, the variance is clearly non-constant. The amplitude of the fluctuation is relatively small in the early years and expands significantly in the later years, forming a funnel shape, as you can see. So the data is definitely follow a multiplicative models. For task B, because the data has both trend and seasonal patterns, so there are 3 proposed forecasting methods. The first one is winter seasonal exponential smoothing, as this forecasting technique is designed to handle data containing both trend and seasonal components. The second one is classical decomposition, as this method is selected to analyze the data with the seasonal patterns, allow user to decompose time series into separate components. And the last one is exponential trend model, because this time series plot visually show that there's a growth at a rate over time. So in order to determine the best forecast methods, firstly we look at the accuracy measurements, and from the data we can see that Winter's methods clearly show that it's the most suitable methods for this data, as it has lowest values across all metrics, MAPE, MSE, and MAD. And the second best method is classical decomposition. Although its MAPE is slightly higher than the trend model, 9% compared to 8%, its MSE is roughly half that of the exponential trend model, approximately 100,000 compared to 214,000, showing that the exponential chain is the least compatible forecast model for this dataset because the gap value between MAD and MSE is much larger compared to the other methods. And for furthermore investigation, I draw a 4-in-1 residual plot for winter methods and classical decomposition methods. So from the figure, you can see that winter methods has the best result, as the normal plots show that the residual closely follow the straight reference line, and the histogram display a bell shape, center as 0, indicating that the errors are normally distributed. For the classical decomposition methods, in plot it is nowhere good compared to winter methods. At its residual plot display a clear wave patterns, providing that the model failed to capture the seasonal components, and the residual versus fit plots show a funnel shape, indicating that the errors increase as the cell grow. So from the analyzing of the error stats and plots, we could see that Winter's methods is clearly the most suitable forecasting methods for the given data. So this is the forecast value of Winter's methods for period 405, 46, and 47. So it is possible to check the confidence interval that predicts today's value, which is 95%, meaning that we are 95% confident that the actual cell will fall between the lower value and the upper values. This interval accounts for the uncertainty in the model and provide a range of probable outcome instead of a single point estimate.
Moving to the task 3, first we select 5 independent variables from x1t to x5t. So we have chosen that the advanced retail sale of food service and drinking place for grocery store, health and personal care store, US import goods by custom basic from Vietnam, retail stores, restaurant, and other eating place. And time series from January 1992 to August 2025 with a data length of 404 observations. Next, we generate the X60 by random uniform distributions in Minitab using the count and random data uniform lower endpoint from 0 to upper endpoint 10. And we could record 404 observation data in the columns. And next, we will record the number into text and record in the CPI category columns following the rules that lower than 4 is good, 4 to 8 is warning, and larger than 8, lower than lower or equal 10 is bad. And we could we see that we will receive 150 value of good, 164 value of warning, and 60 value of bad. Next, we perform a multi-layer regression with A versus X1 to X6, and from the figure we obtain the very high R square 94.66%. It is a very good R square level, but we still need to check if there is the overlap or multi-correlatority in the next sections. Next, we analyze this of variance. First, we would see the regression p-value is lower than 0.05, so the overall regression model is statistically significant. At least one X will help explain it. Why? And the F value is very large, so it could describe the variation in E compared to the random noise. Next is the coefficient analysis. From the table, we could observe that the p-value of x6 is higher than 0.05 and VIF of all variable are violated. So we use stepwise regression with the alpha equal to 0.05. After run the first step, we could see that the x6 had been excluded from the model, but the coefficient x1 to x5 still remain in the model with a very high VIF. So we continue to use step y with the alpha equal to 0.0009 for the regression set of x1 to x5. This alpha is carried based on the experience. Next, after we run the model, we could observe that the model is now good with two coefficient level 6 to x4, but the VIF still in consider range larger than 5 and lower than 10. This is so far the best value. So we will move to the residual plot for E. We could see that the normal probability plot in the follow normal rules, the versus fit and versus moral orders are in the funnel shape, which is the typical errors of a residual distribution. So we consider bulk cost transformation or standardizations to reduce the lack of fit. After we have run the bulk cost transformation with the lambda optimized in the minimize tab and the standardization, we could see that the normal probability plot seem to be improved. Residual have zero mean. The spin was statistic approximately 1.78, which is the residual autocorrelation is acceptable. But the fitted value spot is still violated the homoscedasticity, and this is so far the best fitted model. So in conclusion, the model regression of X2 and X4 is the best fit model so far. Or in other words, the retail sale of grocery store and the US input costs by custom with basic from Vietnam have a linear regression with the sale of BS and Y stores.
Okay, so we're gonna forecasting the Y by using the ARIMA approach. So first we're gonna plot a ACF and PACF to determine the order of the AR and MA. So the ACF show the trend and seasonal pattern with the seasonal index is 12. The pattern is not show cut up like die out, so we can conclude the degree of the AR. The PACF show a die out, but there's a few spike at 10 and 12. So we can also not provide the clear indication of MA order. So we're going to use a tool called the key filler to consider if the data is stationary or not. So the p-value is 0.986, which is failed to reject the new hypothesis. So the data is not stationary. So we're going to differentiate it. So because the data is trend and season, so we're going to differentiate two tabs. The ACF and BCACF still not have a pattern of dial or cut off. So we're going to determine the order of the AR and MA. So we're going to use the tool called forecast with best ARIMA model. P-value in the Q and P is larger than 0.05. So the coefficient of Q and P uppercase is not statistically significant for the model. And also the best model here is 212111 with the season is 12. So we're going to consider chi-square. The long box Q statistics compute for the group of 24, 36, and 48 lag are significant. So the model is considered inadequate if we forecast in the long term, which means that we can forecast about over like 12 months. It's going to be inadequate. So we're going to choose another ARIMA model to have comparison. Based on the reverse model checking and the second best ARIMA model, we're going to adjust the model to 210011 with season 12. So the mean square of the second ARIMA is larger than the previous one. The p-value is smaller than 0.05 with all of the group of lags. So the model is considered inadequate for all of the long-term, short-term, or middle-term forecast. But the ratio plot for both ARIMA is quite good. You can look at this slide. It's not funnel shape in the versus split plot. The residual is following Norman for both methods. But the sum of square for the second is larger than the previous one. So we're going to choose the ARIMA 212111, which is season 12, is the best for fit model. So this is our focus on the next 5 period for that ARIMA model. Thank you for listening.